Section 3.1 is all about injectivity and surjectivity. We're going to learn what it means for a function to be injective or surjective or both. So let's start with some definitions. Suppose you've got a function from x to y. We say that f is injective, or maybe one-to-one, if whenever f of x1 is equal to f of x2, then you always get x1 equal to x2. If the values agree, then the inputs agree. In words, and this is a little bit tricky to parse, I think, each element of the image has a unique pre-image. And to make sense of that, you'll need to remember that the image is the subset of the codomain given by applying the function to everything in the domain. So just see what you can get if you apply a function to everything. And I'm saying that each element of that, you've applied the function to everything in the domain, each element of that has a unique pre-image. There's only one thing that went there. You never have the case that two separate values of the domain map to the same value in the codomain. You don't have that. That's what it means to be injective. One-to-one is quite an evocative phrase, but I would only use the phrase one-to-one. There exist these other phrases, one-to-many, and many-to-many, and many-to-one, and I wouldn't use any of those because it's not obvious to me what they mean. But one-to-one means, I think, for each of these, it's one of those. Right. If in doubt, refer to the definition. If the function values agree, then the inputs agree. That's injective. We also have this word that f can be surjective, or onto, if for every y in y, there's an x in x such that the function on x takes the value of y. You reach everything in the codomain. In words, the image of the domain is the codomain. Maybe you remember one of my warnings was that some authors use range for what I would call the codomain. Well, here's a case when the function is surjective where we agree. Because if the function takes all of the values in the codomain, then I would say that the image there is everything is the codomain. So if we're just talking about surjective functions, then everyone agrees. The range really should be all of the things in y. Okay, so these are two new words, I think, injective and surjective. I'm going to try and stick to injective and surjective being the words I say, but you're welcome to think of them as one-to-one and onto, respectively. Personally, I find one-to-one quite confusing to think about. Maybe you heard me pausing quite a lot when I was talking about it earlier, but I find onto quite helpful, even though it's a little bit grammatically funny. But I find onto helpful. The idea is that the function maps onto everything in the codomain. Here's some pictures. Oh no, I've got another word to define first. Can't move on until I've told you about bijective functions. So a function is bijective if it's both injective and surjective. So in this case, each element of the codomain has a unique pre-image. And that's brilliant because at the start of this, for the functions we were talking about in the previous video, each element of the codomain, well, there might be all sorts of nonsense in the codomain. We don't know if that's got a pre-image or not, or pre-image could be loads of things. So each element of the codomain having a unique pre-image is kind of two claims, that each element has a pre-image and that pre-image is unique. A bijective function is called a bijection. They are very important, so it's worth remembering both of those words. People might say injection and surjection for an injective function and a surjective function, respectively. I think those are less common, but a bijection is a very common name for a bijective function, which means both that it's injective and surjective. Right, okay. Now some pictures, here we go. So I've got all four possibilities, I think, between sets x and y, which are different in the different cases. So in my first picture, I I have a bijection, a function that is both injective and surjective. So quick check, is it surjective? Does everything in y have a preimage? Well, yes, each thing in y does have a preimage. There's at least one arrow pointing at it. So that's surjective. Is it injective? Well, the question there is, do you have two arrows pointing at the same element of y? No, you don't. So it is injective. Good. So it's injective and surjective. And then I've tried to illustrate what might go wrong. So in B, I have a function that's injective, but not surjective. So not surjective because this point in the codomain doesn't have a preimage. But okay, it is injective because it's never the case that the arrows collide. You never have something where different values of x1 and x2 have the same value of f. Okay, picture C, I've tried to draw something that is surjective but not injective. So surjective because everything in the codomain has a preimage, but not injective because there's this point here where there are different values of x1 and x2 not equal to each other that have the same value of f. So this is not injective. If you like, everything in this set has a preimage, but not unique preimage. There's a problem with that one over there. And then just for completeness, in D, I've tried to draw an example where it's not surjective and it's not injective, just to illustrate that functions can do loads of things. They can do all sorts of stuff. So the first one is a bijection. They're my favourite. These two are not quite so good, and then this one is terrible. If you want to put some spin on it. Okay, we've got some more examples though using some of those functions that we had before. In the previous video, we talked about a function defined on real numbers that rounded up to the least integer greater than or equal to that number. That's surjective because it maps onto every integer. In particular, I mean, choose your favourite preimage, there are loads. But for every integer, if you round up that integer, then you get that integer. That looks like a silly claim, but I'm trying to show you that there is a real number. There is a real number such that when you round it up, you get whatever integer you were thinking of. But it's not injective because there are other elements, so if you like x1 and x2, for which the function agrees, you get these collisions. And this happens quite a lot, infinitely many of these examples. Just one would be enough. That even the example I've typed up here is infinitely many examples. I really just need one. So rounding up 1/2 gives you the same thing as rounding up 1, even though 1/2 and 1 are not the same thing. So that's an example with f of x1 and f of x2, where x1 and x2 are not the same. There's infinitely many here because of the n. We've seen from those little diagrams that just having a single problem is enough to scupper your chances of being injective. Do we have some more examples? Yes, we do. We have all of those squaring examples. So this one, from reals to reals, we've seen at length that this is not injective because different numbers square to the same thing. We've got a name for that now. We say the function is not injective. It's also not surjective because it doesn't reach everything in the codomain. There's no real number you can square to give -1. So you don't reach that part of the codomain. So injective, remember, is about collisions. Surjective is about being onto everything in the codomain. We had this function though, where I've modified the codomain. It's still not injective because we've still got that problem about the square of 1 and -1 being the same. But this is surjective because I've clumsily, in a way, just removed all the problems. All those negative numbers have been removed from the codomain so that I can now say everything in the codomain has a preimage. It's not a unique preimage, but it has a preimage. So we say that is surjective because I now map onto everything in the codomain. You can always do a trick like this, I suppose, that if you have a function from x to y, then you can modify the codomain to be the image of the domain, which replace it to construct a new function where magically you do map onto everything in the codomain because you just removed all of the problems. So you can do this trick in general if you have to. Here's another function where I've modified the domain this time. So I've chosen to only look at positive numbers, or 0, and square those. And this is not surjective. We started with a function that wasn't surjective. And it's not surjective. I haven't solved the problem about the square root of -1. There's still points in the codomain that I don't map to. But this time it is injective because I have slightly clumsily restricted the domain of the function so that I've got a unique value for each of the values in the image. Let's say it again. I've got a unique value of the pre-image for each value in the image. I've got negative numbers on the right hand side and I haven't solved that. I haven't got any pre-images of those, but that's fine. Injective only worries about cases where you have more than one value of x that maps to the same point. It's not worried about places where you have no values that map to there. It's worried about excessive numbers of x values that map to the same point. And then finally F4, I thought I'd give you an example of a bijection where I've taken numbers that are non-negative, and if I square them I get numbers that are non-negative, and that is one-to-one properly, isn't it? That for every number in the domain there's a number in the codomain, and also for every number in the codomain there is a unique number in the domain. This function is both injective and surjective. You'll never have the case that x1 and x2 different numbers map to the same point, and for every number in the codomain I can find you a number in the domain. Okay, so I want to show you another definition of cardinality now, using these bijections that we've got, because this definition is much easier to work with than the recursive definition we had before. So here it is. It's definition of finite sets and cardinality of finite sets at the same time, using bijections. So here we go. The empty set is defined to be finite and have cardinality 0, like we said before. And a non-empty set is said to be finite with cardinality n if and only if there exists a bijection from your set to the set, and then I've got 1, 2, 3, 4, 5 up to n. So if there's a bijection from S to those numbers, then we say that your set has cardinality n. If you feel like you've seen this before, it's because this describes the process of counting that you've been doing since you were very small, where you take the elements of your set and you find a bijection from those elements to the counting numbers on the right there. And the rules of a bijection are exactly the rules of counting. You have to make sure that that function is injective, which means that you never have two elements going to the same number. When you say 1, you only point at one object. When you say 2, you point at a different object. And as the surjective, you don't skip out any numbers along the way. You hit all of those numbers from 1 to n, no gaps. So those rules of counting are the rules for a bijection from a finite set to that set of counting numbers. And you can use that as the definition of the cardinality of a finite set, expressed here in terms of bijections. You might like to convince yourself that this does exactly the same thing. It has the same outcome as the recursive definition that we had before, if you like. So for finite sets, the cardinality matters if you're looking for injections and surjections. You might have worked out way back at those diagrams that I showed you with the 4 pictures going across the screen that a function can only be injective if the codomain is at least as big as the domain. So if you have a set of elements x and you're trying to map them to y, and your rule is that you're trying to make an injective function. Injective function is not allowed to repeat any values. Then you're in big trouble if your codomain is too small. This is called the pigeonhole principle. The thing that to imagine, if you want to think about the pigeonhole principle, is the idea that you have lots of pigeons and they live in these little squares called pigeonholes. And the rule about injections is that you can't put two pigeons into the same pigeonhole. They don't fit. So then the result is that if you want to set up an injection from pigeons to pigeonholes to put all of the pigeons to sleep, then you need to make sure that you've got at least as many pigeonholes as you have pigeons. That the size of the codomain is at least as large as the size of the domain. You're allowed to have spare pigeonholes. The word pigeonhole has survived, even though carrier pigeons for messages sort of haven't. The word pigeonhole survived in the context of a mail room. So if your college has a room full of post with separate places for each person's post, then you might find that they're called pigeonholes, even though there aren't any pigeons to be found. And you might like to check that there are enough for all of the people in your college. Injections. Right, so similarly, a function from x to y, and I might not spell this one out so much, can only be surjective if the other way around, the cardinality of y is less than or equal to the cardinality of x. If you have to reach everything in y, then let's hope there's not too many things in y. So if f is bijective, then both. So the cardinalities must be the same. So this gives you a relation between sets to say the domain and the codomain of a bijection must have equal cardinality. That whenever you have a bijection between finite sets, they must be sets of the same cardinality. This gives us a way to talk about cardinality in general without thinking about counting, and it's a version of this that lets us talk about the cardinality of infinite sets. So we say that sets have the same cardinality if there's a bijection between those two sets. And there's a system of naming these, but let's focus for now on the idea that two sets have the same cardinality if you can find a bijection from one to the other. And this leads to the conclusion that the naturals and the integers and the rationals all have the same cardinality. You might like to go and try to find bijections between those sets, if you can. So it's a challenge to prove that those have the same cardinality. But then surprisingly, the reals doesn't have the same cardinality as those sets. And even though it's another infinite set, there's no bijection between the naturals and the reals. That's a fact that you will see proved before the end of Priadam's mathematics, but you might like to experiment with what's going on there. And several videos ago, I hinted at the idea that this definition of cardinality doesn't just ascribe a single size to infinite sets. There are different sizes of infinite set. You'll find out more about that in other courses to come. So that's the end of this section, but next time we're going to think about the composition of functions, and we're going to see how these properties, injectivity and surjectivity, transfer to the composition of one function after another. See you there.